Opening hook, the problem. Visual, black screen. Slow fade-in of archival newspaper headlines. Fusion breakthrough. Unlimited energy soon. Dates changing from 1970, 1990, 2010, 2024. For over 70 years, fusion power has been described using the same sentence. It's about 30 years away. That prediction was made in the 1950s. It was repeated in the 1980s. It was said again in the early 2000s. And today, right now, you will still hear the exact same claim. This isn't because fusion scientists are dishonest. And it's not because progress hasn't been made. It's because fusion runs headfirst into multiple, non-negotiable laws of physics. And every time engineers solve one problem, another one appears underneath it. Visual, simple equation fades in. Fusion is easy on paper. Fusion is brutally difficult in reality. Today, we're going to explain why. Not the hype, not the press releases, but the engineering constraints that keep fusion permanently just over the horizon. Section 1. The context, why we want fusion. Visual, global energy demand graph rising steeply. Human civilization runs on energy. Modern society depends on electricity, industrial heat, fertilizer production, data centers, transportation, and global demand is still climbing. Visual, comparison chart, coal, oil, gas, solar, wind, nuclear. Our current options all have serious downsides. Fossil fuels emit carbon. Renewables are intermittent. Fission nuclear is politically radioactive and produces long-lived waste. Fusion promises something close to a miracle. No carbon emissions. No meltdown risk. No long-lived radioactive waste. Fuel derived from seawater. Visual, animation of hydrogen atoms fusing into helium. Fusion is the process that powers the sun. If we could replicate even a tiny fraction of that process on Earth, energy scarcity would effectively end. So why haven't we? Section 2. The first physics barrier, the Coulomb wall. Visual, two positively charged nuclei repelling each other. Fusion requires smashing two atomic nuclei together. But there's a problem. Atomic nuclei are positively charged. Like charges repel. This repulsion is called the Coulomb barrier. To overcome it, nuclei must collide at extremely high energies, which means extremely high temperatures. How high? Visual, temperature scale. Surface of the Sun, 500 degrees C. Core of the Sun, 15 million degrees C. Fusion reactor on Earth, 100 to 150 million degrees Celsius. Not because fusion likes that temperature, but because physics demands it. At lower temperatures, fusion reactions are too rare. Energy output drops below losses. The reaction dies. So the first challenge of fusion is simple to state and almost impossible to solve. How do you confine matter hotter than the core of the Sun without touching anything? Section 3. Magnetic confinement. Holding fire with fields. Visual, tokamak reactor animation. You cannot build a container for plasma. No solid material survives contact with plasma at 100 million degrees. So fusion engineers cheat. Instead of physical walls, they use magnetic fields. Charged particles follow magnetic field lines, so strong magnets can trap plasma in midair. This leads to the most famous fusion design, the tokamak, a donut-shaped magnetic bottle. Visual, field lines spiraling inside tokamak. In theory, this works beautifully. In practice, plasma is not cooperative. Section 4. Plasma instability, the real enemy. Visual, slow-motion plasma turbulence simulation. Plasma is not a gas. It's not a liquid. It's a chaotic, electrically charged soup. At fusion temperatures, plasma forms turbulence, creates instabilities, develops ripples and waves, leaks energy constantly. This energy leakage is deadly. Fusion only works if energy produced, energy lost. This balance is captured by the Lawson criterion. Visual, Lawson criterion triangle, temperature, density, confinement time. To achieve net energy gain, you must satisfy all three. High temperature, high particle density, long confinement time. Improve one, and the others fight back. Increase temperature, plasma becomes more unstable. Increase density, reaction walls heat up and erode. Increase confinement time, small instabilities grow into catastrophic disruptions. Fusion isn't one problem. It's three problems tied together. and solving one makes the others worse. Section 5. Superconducting magnets. Materials hit back. Visual. Close-up of superconducting coils. To confine plasma, you need extremely powerful magnetic fields. Those fields require massive currents. Superconducting magnets. Cryogenic temperatures near absolute zero. Let that sink in. Inside a fusion reactor, the plasma is hotter than the sun. The magnets are colder than deep space. They sit meters apart. This is not poetic. It's an engineering nightmare. Visual. Temperature gradient graphic. And superconductors are fragile. They lose superconductivity if overheated. Are sensitive to radiation. Crack under mechanical stress. A single plasma disruption can dump heat into the reactor walls. Induce currents in the magnets. Cause a quench, instantly destroying superconductivity. When that happens, stored magnetic energy releases violently. Fusion reactors must be built like pressure vessels and particle accelerators at the same time. Section 6. Neutrons, the silent material killer. Visual. Fusion reaction releasing neutron. Fusion reactions don't just release energy. They release high-energy neutrons. Unlike charged particles, neutrons ignore magnetic fields, slam directly into reactor walls, damage atomic lattices. Over time, this causes embrittlement, swelling, microcracking, loss of structural integrity. Visual. Microscopic lattice damage animation. This means fusion reactors don't fail dramatically. They wear out invisibly. Current materials can survive months to a few years at best. Commercial power plants need decades of reliable operation. Right now, materials science, not plasma physics, is one of fusion's biggest bottlenecks. Section 7. Tritium, the fuel that doesn't exist. Visual. Hydrogen isotopes chart. Most fusion designs rely on deuterium. Deuterium is abundant. Tritium is not. Global tritium supply today, less than 30 kilograms. Fusion power plants would need several kilograms per year per reactor. So fusion reactors must breed their own fuel. Visual. Lithium blanket concept. Neutrons strike lithium, produce tritium. In theory, this works. In practice, tritium leaks. Breeding ratios are marginal. Extraction systems are complex. Tritium is radioactive and regulated. If tritium breeding fails, the reactor shuts down. No fuel, no fusion. Section 8. Net energy gain, the misunderstood milestone. Visual. Net energy gain headlines. You've probably heard headlines like, "Fusion achieves net energy gain." This is technically true and deeply misleading. Most announcements refer to Q greater than 1, meaning energy from fusion energy delivered to the plasma. But that ignores magnet power, cryogenics, control systems, heat extraction, power conversion losses. Visual. Energy flow Sankey diagram. When you count everything, no fusion reactor has ever produced net electricity. Not once. Fusion has crossed scientific break-even. It has not crossed engineering break-even. That gap is enormous. Section 9. The economics. Why working isn't enough. Visual. Cost comparison bar chart. Even if fusion worked perfectly tomorrow, it still faces one brutal question. Is it cheaper than the alternatives? Fusion reactors are massive, complex, custom-built, maintenance-heavy. Meanwhile, solar costs have collapsed. Wind is cheaper than fossil fuels. Batteries improve every year. Fission reactors already struggle economically. Fusion doesn't just have to work. It has to work cheaply, reliably, and at scale. Physics doesn't care about venture capital timelines. Section 10. Why it's always 30 years away. Visual. Timeline looping back on itself. Fusion research is real. Progress is real. Breakthroughs are real. But each breakthrough reveals new material limits, new stability problems, new cost barriers. Fusion isn't delayed because engineers are slow. It's delayed because nature is unforgiving. Every solution creates new constraints downstream. Final verdict. The truth about fusion. Visual. Calm, slow montage of fusion labs. Fusion is not impossible. It is extraordinarily difficult. It may work someday. It may even work this century. But fusion is not a silver bullet. It is not a climate emergency solution, and it will not replace existing energy systems overnight. Fusion teaches us something deeper. Human ingenuity is powerful, but it does not rewrite physics. The future of energy will be messy. It will involve trade-offs, and it will likely arrive through many imperfect solutions, not one perfect machine. Fusion may eventually earn its place among them, but until the laws of physics change, it will probably remain about 30 years away.